So, in this module we will start to familiarize ourselves with some basics of design. Now, so far what we have done is modeling and lots of analysis of the system, analysis in terms of stability starting from the Routh criterion. The root locus gave us lots of other information about how my closed loop systems change as I vary the gain from 0 to infinity. There is also a parallel of what to do for gains from 0 to minus infinity. It's a straightforward exercise, but we will keep that for a little later, and that is not important at the moment. We also saw analysis in the frequency domain. We characterize relative stability in terms of the gain and the phase margins. So, what we will do now is to slowly learn concepts of design. Now, what are typical design problems? So, while we were doing time response analysis or even the frequency response analysis, we had some basic parameters or basic things which we observed, like the rise time, the settling time, the peak overshoot, and we saw how all these were related to the natural frequency and the damping. Similarly, the frequency domain concepts like the bandwidth, the resonant frequency were also in a way related to these system parameters. Now, any design problem would be based on setting these values like the peak overshoot or the rise time or the settling time, the steady state error to some desirable numbers. Now, that is what we will focus on how do we go about doing this. So, there are three basic elements in this control design. So, we start with the proportional controller, the integral, and then the last would be the derivative action. So, okay. So, let us slowly go through these things, right. So, we started defining in our earlier lectures a closed loop system of the form of this form where I had a plant to be controlled via this controller. I have a reference signal R of S which I need to track here, then there was disturbances in the system, there was noise and so on, right. So, this feedback configuration we saw is capable or it does improve the stability. It also in some sense helped in meeting the performance specifications. We will elaborate on this a little more shortly. We also saw how feedback helps decreasing the sensitivity to certain parameter variations of the system. Disturbance rejection was also very obvious while we were doing the feedback control, and of course, attenuating of the measurement noise and so on, right. So, of course, what was the defining factor even when we looked at the error constants was this signal E of S, right. Okay. So, a typical first order system with some time constant t looks something like this, right. G1 is 1 over 1 plus Ts, right, and then its response was typically like this, right, depending on the time constant how fast or how slow it was, and it had also inherently some steady state error. So, this is u of t and this is okay, let me call this y of t or c of t depending on whatever terminology or notation we are using. Okay. The second order system was of this form. I had the natural frequency omega n square, I had the damping ratio zeta and so on, right. And for a second order system we defined some basic properties like the rise time, again it was depending on zeta and omega n. The delay time was also depending on zeta and omega n. Similarly, the peak overshoot was only depending on the zeta, and the settling time again both on zeta and omega n. Okay. So, typically any performance metrics are defined in terms of these 4 or 5 things which we defined here: rise time, delay time, settling time, overshoot, and sometimes also the steady state error. Okay. Now, if you see that all these were defined only for second order systems, and typically you may say, well, not all systems we come across are second order systems. It might be we actually saw third order systems. We also did examples where we had system with 7 poles and so on. So, how do we translate this situations or these design parameters or performance metrics to cases where we have say several poles in the system. Okay. So, let us say I have a configuration like this, right. I have these 2 poles here, I have these 2 conjugate complex poles here, a pole here and a 0 here, right. So, this is something which has like 1, 2, 3, 4, 5 poles and a 0, right. So, say well what is the contribution of the poles and zeros to the response of the system. So, we can say that these 2 poles, right, I call them as the dominant poles of the system, because this as time increases the response of this it dominates more than these 3 or 4 guys over here, right. So, we will see actually I show you some plots and then also we will do some analysis on this, right. So, let us first start by analyzing the system where there is an extra pole or 0 along with these dominant poles, and I think over the next few slides I think this concept of dominant poles should be more or less clear. Okay. So, we start with a typical second order closed loop system and we know that this is always stable. So, we do not need to worry about stability here, and just for computational purpose or for simplicity I say well I set the damping ratio to 0.5 and omega n is 1. Now, I will start by investigating what is the effect of adding a 0. So, where do I add the 0? Let us say I add a 0 at s equal to minus a, again in the left half plane. Well, I just do a little manipulation here just to maintain the DC gain at 1. Nothing really changes, but just for things to look a little neat, I just add divide this s. So, the way I get this is as follows. So, if I just use the 0 as s plus a, my DC gain would be a, right, and I just want to make it 1. So, I will just do s plus a by a for which the DC gain is 1. Okay. So, the response would now how will my transfer function now look like? C1 of s is this guy, the 0 at minus a, in such a way that the DC gain is 1 divided by this guy, and I will get something like this, right. So, I have the original thing. So, when zeta equal to 0.5, omega n equal to 1, this guy just becomes 1 over s square plus 2 times 0.5 times 1. So, that is s plus 1. Okay. So, now look at something interesting here, right. So, this is my original transfer function which is already here, and then what happens to transfer function if I add this s over a plus 1? Well, I still have this guy in the denominator and a numerator at s, and we know what is the idea of this s, right, in the Laplacian domain. It has just to do with differentiation. Loosely speaking, multiplying by s would mean differentiating that particular signal, right. And therefore, if I write it in terms of in the time domain, C1 of t is C of t, like the inverse of this, plus 1 over a C dot of t. Okay. Now, what happens to the response? Well, this just for simplicity take the step response. So, y of s is C1 of s, right, over C1 of s with the step, unit step has a Laplace of 1 over s. So, this is Cs over s plus s over a Cs by s, right. So, where does this come from? This is something here, right. So, this is if I were just to write that properly. So, this would be in C1 of s is C of s plus s over a C of s, okay, and that is what happens here. Okay. So, this is y1 of s plus s over a y1 of s, right. So, I will just define the output corresponding to the original plant C1 as y1. So, now I go back to the inverse, do the inverse of the Laplace, go back to the time domain, and what I have is y of t is y1 of t, the original response without a 0, plus 1 over a y1 dot t. Okay. So, when So, I just denote y1 dot as y2 and the total response is y of t is y1 plus y2. So, let us I can just remember this for a while. Y1 is the original response without the 0, y2 is just the response of the 0 of adding the 0 and then y of t is the total response. Okay. So, if I just take this system and I say I add a 0 at s equal to minus 0.5. Okay. So, what was my original response? I am calling this as y1 of t. So, this is the signal in the black, right. This is y1 of t. Now, I add a derivative term and what does or sorry I add a 0 and what the 0 does is adds this extra term into the response 1 over a y2 of t. What is y2 of t? y2 of t is y1 dot of t. Okay. So, the total response y which was y1 plus 1 over a y2 is just y, this red line here. Okay. So, the black line or the black curve was the original response. I add a 0 at s equal to minus a and then I get this one again by maintaining the 0 maintaining the DC gain to be 1. Okay. So, this is at s equal to minus 0.5. So, where were my original poles of the system? The original poles of the system were at minus 1 plus minus j square root of 3 this entire thing divided by 2. So, I have something here. So, this is my minus 1, I will have minus half plus minus root 3 by 2 somewhere here and here, right. So, these two are the poles of the system and I am just adding a 0 over here. And this is again the sigma and the j omega axis. Okay. Now, I say I add a 0, I remove this guy and I add a 0 over here at s equal to minus 1 and I remove this guy, right, this guy no longer exists. So, what I have is the second order system plus a pole at plus a 0 at minus 1. Okay. So, again we follow the same thing and see what happens to the response. The response in the black remains as it is. Okay. The scales are different and therefore, this looks a little bigger, right. Okay. Now, y2 looks like this, which is 1 over a y1 dot and the overall response now is something like this, okay, the red line. Now, what do I do is I just remove this 0 over here and I say I add a 0 much further away, right, say somewhere here I say this is a 0 at minus 8. Okay. Now, what happens? Well, y1 just still remains the same, y2 well the blue line does something like this and then I have the total response is something like this. Okay. Now, again let us compare these 3 plots, right. So, as the 0 is closer to the origin, you see a difference is quite big here, right, between the original response in the black curve and the red and the response in the red, which is the effect of adding a 0 at s equal to minus 0.5. If I add a 0 at s equal to minus 1, well there is still some effect, but the curves get much closer. I add a 0 further to the left, right, at very far at s equal to minus 8, see that the response is more or less the same. In a way I can just say, well I just do not add the 0, right, and nothing changes. Okay. So, apart from this distance in the curves here, what else do we observe? What is the difference between this black curve and the red curve here? Well, one thing is obvious that this has an increased overshoot. Okay. Now, here so the steady state value was 1, so my overshoot is like almost between 60 and 70%. Okay. This is at 0 at minus 5. Now, here the pole is the 0 is slightly to the further to the left. So, the overshoot still increases, but not by too much. Okay. But here well it is more or less the same. Well, first is an increased overshoot depending on the location of the 0, but what happens here, right, there is no too much change in the settling time, and it must see they more or less reach to 98% of the original value in fairly the same time, right, all 3 guys including the original one. And then, well, what is good here is that I have a faster response, in a way that I reach the peak time much faster here. Here I was taking about 2.5 seconds, here I reach in less than 1 second. Similarly, here also the response is faster, right? I reach this time, which is like 2.5 seconds. Here I reach about little over 1 second, and so on, right? So my response is faster, and as I keep shifting or pulling my 0 further to the left, and I keep doing this, what I observe is that as A goes further to the left and furthest, then the contribution to the 0 or the contribution of the 0 to the system response decreases, and we get back the original behavior. Say this is minus 80, I do not really need to plot this curves also, right? It will just be almost exactly be the same, right. So, there is some effect of adding the 0, and it is based on where we add the 0. So, we want them somewhere close to these guys to see the maximum effect. Of course, there are also drawbacks here, right, about that, in a way that the overshoot actually increases, but nothing changes in the settling time. Okay. Now, what if I add a 0 in the right half plane, right? Again, we do the same thing, that to maintain the DC gain at 1, we just divide the entire thing by A. So, my transfer function of the system is now 1 minus S over A. It's again looks very the same. I have 1 over S square plus S plus 1. I just have a minus here, minus 1 over A, 1 over S square plus S plus 1. Or in other words, C1 of t is Ct minus 1 over A C dot. We had a plus earlier. So, similarly, the response will also translate in the same way, that the total response is the response y1, and then in addition we have this response due to the 0 that is placed at S equal to A. Okay. So, what is happening here? Well, again the black curve is as same as in the previous case. The blue curve is the effect of adding a 0 on the right half plane. Now, the red curve, which is the combination of these two, looks something strange now, right. So, initially if you look at this plot, you might see that, well, what do I want to reach? I want to reach the point plus 1, right, in, well, with less number of overshoots, and settling time should be fairly small, and also no steady state error. But what am I doing is, initially if I just switch this on, and I see that, well, I am actually going away from 0, which might mean, well, I just want to stop it over here, because I think, well, the system is doing something very weird, right. But then if I just let it go for a little while, it reaches the minimum here, and then it actually starts going up, and then does something same as the previous one, that there is some increased overshoot. Of course, there is nothing much in the response is a little slower, the overshoot has increased, and of course, the settling time does not do much things. Okay. So, what is the first observation is that, well, so far we have only analyzed overshoots, right. How much? So, I start from 0, my desired value is 1, how much do I overshoot before settling down at 1, right. So, that is over here, right. This was the overshoot. Now, in addition to that, we also experience something called an undershoot. I go down from minus 5 till this almost minus 0.8, and then come back here, right. And then this undershoot, what it does is that it actually increases my delay time, the rise time, and the peak time, and so on, right, which means that my response is quite sluggish now. So, when poles and zeros are in the right half plane, these are called non-minimum phase poles and zeros. We defined this last time, and we will still stick to that definition, that if all the poles and zeros are to the left, then it is a minimum phase system, and if some guys sit to the right, it is a non-minimum phase system. Okay, we will deal with this when we when we talk about design in frequency domain, or there will be some special module on just dealing with right half zeros. So, at the moment we will just restrict ourselves to this definition, that will be enough for our analysis. Just that we just remember that if I have a right half 0, I experience an undershoot, and this will always happen, and I will show you a little proof for that a little later. Okay, so here what we will see is the effect of adding a pole to a standard step response of a second order system. So, well, this the standard response is this one over s square s and 1 and 1 over s. Now, I add a pole, right, I add a pole at different locations a. So, first I see that if I just look at y1, this is a natural response or the response without adding a pole. If I add a pole very close to the origin, then you see there is a significant change in the response. Also good in a way, because I kill the overshoots and other stuff. Similarly, if I add a pole slightly further, maybe like little 5 times to the left, then I see, well, the responses almost look the same, right. There is a very little margin here and so on. Now, if I keep going further, I see that the red line actually touches the black line, right, and that is not surprising, right. So, as a tends to infinity, the contribution of the pole it decreases, and as this pole a keeps on going to infinity, there is no effect at all. So, whenever we do in a design process where we have to add a pole such that it does not have too much effect on the transient response, we take it to be 5 times the real part of the dominant pole, as in the middle case when we have a pole at s equal to minus 2.5. So, we will keep this in mind while we will explicitly talk about design problems, while when we are looking at improving the transient performance or the steady state performance and so on. Okay, so this leads to the definition of or characterization of the dominant poles of the system. So, the dominant poles are the closed loop poles that have dominant contribution on the transient response of the system. And it is quite possible that these occur in conjugate pairs. They could also just be sitting here, right, on top of each other, say at s equal to minus 1. And higher order systems are generally adjusted such that there exists a pair of dominant complex conjugate poles, which in that case we would just restrict our analysis to these 2 poles, and we could do the entire analysis and design, right. But for that, well, it is desirable to have the real parts of other poles and zeros at least 5 times further away than the real parts of the dominant pole. So, if this is minus 1, these guys should be at least at minus 5 and further away. If this is at minus 1 and there is say a dominant, not really dominant, but say some other pole pair at this one, then I cannot really call these the blue guys as the dominant poles. So, these are like typically, because the response of these guys over here, they die down faster. The response of these dies even like little slower than this, but still fast enough. Then this also dies down fast, and what is remaining is just this one, right. And the limiting case is when the poles are here, right, the response never dies down, right. So, this if this plus this is the case, then these are the dominant poles, because this will still die down to 0 after maybe a fairly large time, but this will remain as it is. So, if I look at this in terms of a classroom, the guys who are on the sitting on the last bench furthest away from me go to sleep much faster than these guys, and possibly the dominant guys are the ones who are on the first row or the second row, right. So, it is just like the attention span also, right. So, these guys lose attention faster, these guys a little slower, but these guys possibly are a little more attentive than these other guys. So, if these guys are here, well, they still go to 0, but a little possibly after 45 minutes of the class or something. Okay. And this guy is me here, right, the teacher on the imaginary axis. He cannot go to sleep, right, he will always be talking. Okay. So, now we will see what is the effect of adding poles to the open loop transfer function. So far we were just doing the closed loop one, right, s square plus 2 zeta omega n s plus omega n square, right. Now, we will see what is the effect of adding poles to the open loop transfer function. Well, we will do this in terms of the root locus. Now, the step response sometimes may not give us too much information, but we know root locus actually is a little easier to interpret, and things are much straightforward in some sense to see from the root locus. So, we will switch to the root locus plot, right. So, let us say I just have a g of s is 1 over s plus 2, it is just a pole here. How will the root locus look like? As the gain k increases, it just goes further and further to the left, it's stable all the time. Okay. Now, to this guy I add another pole at s plus 4. So, this is my original pole, I add another pole here, and what I know from the first class of root locus is that, well, this guy will move towards the right, this guy will move towards the left, they meet each other and then they go their own ways. Okay. Now, then I say, well, I will just do some more experiment, right, I will just add at s plus 8. So, I have s at minus 2, minus 4 and minus 8. So, I have 3 guys, all 3 would go to infinity because there are no zeros. This guy will choose the lazy path, go here, these guys have to move, this guy has to move to the right, this guy has to move to the left, because something tells me that a point on the root locus lies on the real axis only if the number of poles plus zeros to the right is an odd number. Okay. Therefore, this is not allowed to be on the root locus. This guy, well, this entire line is allowed to be on the root locus, so he just takes the easy path and just runs away. Now, these two guys meet here, I calculate the angles of the asymptote, that will be 60, then this will be 180 and minus 60. So, these guys will go this way. Okay. So, what is happening, right? So, first, well, the root locus which was just going to infinity in the first case is now pulled a little bit to the right, right. So, the root locus exists just in this domain, it was earlier existing in this entire domain here, right, and I add one more pole and it shifts it further to the right in such a way that it can also go to the verge of instability after I attain a particular value of the gain k, right. So, these are the very simple things, right, there is nothing to actually remember as a formula or anything like that, but just that we are just plotting various things, just kind of just doing some initial experiments to then evolve towards a general theory. Okay. Now, what happens if I add a 0 now to the open loop transfer function? Okay. So, let me say I start with this open loop configuration. So, I have a pole at the origin, a pole at minus 2, a pole at minus 5, and of course, if I just plot the root locus, this guy will go away to infinity, these two guys will meet up each other and then they again go to infinity, and after a particular value of k, the Routh-Hurwitz will tell me that I am going towards the unstable region. Okay. So, let me just add a 0 just slightly towards the left of minus 5, right. So, this was minus 5 and this is a 0. So, this guy which was now running away is now trapped by this 0 here. Not only this, right. So, this guy also does something nicer, he not only holds up this guy here, he also does things in a way that the root locus now is well more or less shifted to the negative region, right. There is no point of instability here because my asymptotes are just the imaginary axis. Okay. Now, I add poles somewhere not really very far at minus 7, but somewhere between these two poles, right, this and this. So, well, this guy again it will just move to the right and stop here, and now I see that the root locus has improved much, because if I were to deal with this gain here, you see that I am close to the verge of instability, right, this and this, right. So, this kind of adding a 0, it makes my system stable because it is pulling this blue and the red lines to the left, but it is well it may not be too good in terms of relative stability. Now, I add a 0 at minus 3 and I say, well, it is actually fairly stable for all values of gain k, right, and if I add it further at minus 1, then I get a configuration which looks like this, right. Okay. So, what does the observation tell us? The observation tells us that the addition of a 0 to an open loop transfer function, it pulls the root locus to the left, right, and the effect of 0 is prominent when it is close to the imaginary axis. Okay. So, in these plots we just start with a third order system and then study several effects, right. Okay. Now, based on these observations we will just start with the basic element of control. One is the first one is the proportional control. It just means what happens if I just keep on adjusting the gain. Does adjusting the gain achieve my control objectives or not, right. You either increase the gain, decrease the gain and so on, and we will see under what conditions just a proportional controller or just by adjusting the gain k we meet our performance specifications. We will also see if there are any drawbacks, right. Just by adjusting the gain, even the system is stable, does it always help us achieve good results. Okay. So, that is what we will do here, right. So, again I have an R of s, the G of s is the plant and my controller is just a proportional controller. Okay. So, as usual this is my reference signal, this is my output, there is a certain error and then the controller is supposed to adjust according to itself based on the error and so on. Okay. So, the first question is when will a proportional controller work? So, the steps we usually do here are the following. Let us say I am given that that my peak overshoot should not be more than 20%. I am also given a specification that the settling time should be say 5 seconds or less, correct, and maybe some other things on TR and so on. So, what this will translate to is some zeta and some omega n. Okay. Now, I just keep on moving my gain from 0 and see at any point of the root locus if these specifications are met, if these are my dominant poles. If it is met at this point and this point, then I say yes, I can just adjust the gain and then that value of gain k would sit in the controller and do my objectives. But if this zeta and omega n translate to this pair of dominant poles, then no matter whatever I do with my gain, I am never here, right. So, when does this work? Well, of course, we have the freedom to vary the gain k, which means we are restricted to move on the root locus, and therefore, this works when the poles of the root locus meet this specification, right. So, I just translate the given specifications into zeta and omega n. These zeta and omega n translate to appropriate locations on the root locus or on the complex plane. If by adjusting the gain I could arrive at those complex planes, then okay, I just say this is my controller with that value of the gain k. If not, well, we need to do something else, right. Okay. So, what else does a proportional control do, right? So, again it just depends on the controller adjusts according to the error and so on. What happens in the Bode plot, right? In the Bode plot, the gain k would just shift the magnitude plot. This does not contribute to the phase remains the same. The magnitude could go like up and down depending on whatever is the value of gain k, okay. Again, so this is the case of an unstable system, could be easily seen here, and we could see that by adjusting the gain I could actually push the Bode plot or the system to the verge of stability.